In this corner here, you see an electron, and the electron is negatively charged. When you have a negatively charged particle moving, say, up and down, okay, constantly, you're going to generate what is called the electromagnetic waves. So here, electromagnetic wave is being generated. So I'm not going to give you the definition quite yet. So think of electromagnetic wave as a pathway in radiation energy is going and using that wave to generate to go to a next point. So here's a formal definition. Electromagnetic wave is a wave created by the movement of the charged particles, and that's going to carry the radiation energy. Now, there are different types of electromagnetic waves. Some are very short like this, and some are very long like this. Now, depending on how the radiation waves how it looks, it's going to generate different electromagnetic wave. And here is a spectrum of electromagnetic wave. Something very short like this, we're looking at gamma ray. Something a little longer would be X-ray, then ultraviolet, visible, infrared, microwave, and we have radio frequency. I'd like to note just few of the images that are above. So let's look at microwave region. In the microwave region, we're looking at a wave that looks very much like this. And we're looking at things like cell phone, your mobile device, and microwave oven. These are all part of electromagnetic waves. Whereas here, this one is more of harmful waves, and then these are like X-rays, right? And then it gets short. And the shorter the wave is, more harmful that wave can be. This entire spectrum is called the electromagnetic spectrum, and it ranges all types of electromagnetic radiation in this data in a line format here. Now, I like to go take a part of a wave, I'm going to take this part over here and then zoom in and talk about the different parts, meaning label different parts of the wave. So here are some parts of a wave. The very top of a wave would be called the crest. The very bottom, the big dip down here, is the trough. The amplitude is the distance midway between the bottom, midway from all the way to the top, or it could be the midway from all the way to the bottom. And amplitude is measured either in meters, nanometers, or it could be any length measurement. It's sort of like you're trying to measure the height of a mountain, right? From the sea level to the mountain all the way to the top. You measure it in meters or miles, right? Any length. And same for here. You're measuring it in meters, nanometers, and that you're going to see, or any length measurement, but you're going to see much more of meters and nanometers. Now, what is this wavelength? Wavelength is represented by a symbol called lambda. So you see this little lambda sign here, and that is the measurement between crest to the consecutive crest. Or it could be from bottom trough to trough. And that wavelength measurement is also measured in meters, nanometers very much often, or it could be any length measurement. And I have mentioned before in the previous slide that the shorter the wavelength, the shorter the distance between the crest to crest. As it shortens, you're looking at this region, and crest to crest longer region, you're looking at more towards here. All right, let's go back and then move on. There is one more part of the wave that's not I wouldn't say you can't really see it. And the best way to illustrate is through this car example. Now, let me read the frequency definition first. So frequency is a part of a wave, and it's the number of wave cycles that pass a specified point in space in a specific amount of time. And the unit is in second to the negative first power, or 1/2 second, or hertz. Let's take this car example here. Imagine this car is going to pass this line in 1 second. All three of the cars are going to pass in 1 second. So let's see. 1, 2, and 3. Although that's not all in 1 second, it's probably much more, but let's just pretend. So 3 cars passed in 1 second. That means the frequency of this is 3 cars over second. Or we can say 3 second to the -1 power. Or we can say this is 3 hertz. Or we can say, we can just write it as 3 instead of the cars, we just write seconds. Let's look at in a perspective of waves. So here I have waves. Okay, a little hard to see, but we're going to focus on the red one. How many waves, okay, will pass through this y-axis in 1 second? So what is actually one cycle of a wave? So one cycle of a wave would look something like this. So if I have a graph like this and I have waves, one cycle of a wave would be this point, and then going up and down, and then back to here. Okay, this point right here, this is one wave. So how many of this cycle passes through this Y? Okay, so let's see. In 1 second, how many pass through? Just focus on the red one. Okay, ready? And 1. And then 2. Okay, so say 2 passed. Okay, say 2 passed. Then we say that hertz, this would be 2/second. Or we can say this is 2 second to the -1 power. Or we can say this is 2 hertz. You can also write it as 2 waves per second. We usually don't write the waves, we don't write the cars either. But this is what a frequency is. Now let's do a learning check. What is the frequency of a boy swinging that completes 18 cycles in 30 seconds? Okay, we know that the frequency needs to have second on the bottom and the cycles go on tops. So frequency, or V, is equal to the cycles over time, and which is 18 cycles per 30 seconds. So take out your calculator and then let's calculate this out. 18 divided by 30. 18 divided by 30. That would be 0.6. So 0.6 cycles per second, or we can write second to the -1 power, or we can do 0.62 hertz. Either one works. What is the frequency of an electromagnetic wave that passes a point with 1.2 times 10 to the 15 cycles in 2 seconds? Try this and come back and check the key. And here is the key.